Any questions? Any questions? Okay, I'll repair. Okay, few of the terminological things that I should clear off. Induced subgraph. For example, you just take the vertex set X. Another thing, I've been using this term neighborhood. Neighborhood of X. This is set of all the vertices y such that xy is an edge. Also, being a bipartite graph is a hereditary property. What does that mean? If a graph is bipartite, then any subgraph of that graph is bipartite. Such properties are called hereditary properties. Yeah, it's like what is hereditary about it? So that it inherits that property. If father has a certain property, then the son or the daughter has the same property. That is the inheritance. Not all graph properties are hereditary properties. For example, being connected is certainly not a hereditary property. That is not true. Just because graph is connected doesn't mean that subgraphs are connected. Even induced subgraphs may not be connected. That is not quite true. Okay? But being bipartite is a hereditary property. Okay, the first problem we want to look at today is this. You're given a complete graph. So this is K4. I want to write this as a union. The H set, I want to write this as a union of subgraphs which will cover all the edges. For example, one way of doing this, so what is the corresponding partition? You have 1 and 3 on one side and 2 and 4 on the other side. Take all possible. Yeah. Have I exhausted all the edges? No, I'm still left with the edges 1, 2 and 3, 4. Therefore, the given graph is not bipartite, K4 is not bipartite, and I want to write it as a union of bipartite graphs. I want to write K4 as a union of bipartite graphs. My claim is you need at least 2. You need 2 bipartite graphs to write this as a union of bipartite graphs. So what would be the, so I still want to, so 2 bipartite graphs are sufficient to cover all the edges. There is a repetition here, namely the edge 1, 3 has occurred there as well as here. Any other edge? 2, 4. Yes. So this is not a decomposition. This is not quite a decomposition that we talked of yesterday. You just want to exhaust all the edges using least number of bipartite graphs. And what we want to say is you really cannot do this with, clearly you cannot do this with one bipartite graph, that's clear. If you can do it with one bipartite graph, it's as good as saying that the given graph itself is bipartite. That is not true. It is not bipartite. And 2 is minimum number. In general, the kind of statement we want to prove K bipartite graphs if and only if proof induction on K. What happens when K is equal to 1? Is this a bipartite graph itself? K2 is a bipartite graph. K3 is not. K2 is a bipartite graph. And so you're quite all right. This itself is a bipartite graph. So I can now assume that, so that's the basis of induction. I can assume that the result is true for K minus 1 and try proving it for K. Let K be at least 2. So first let n be less than or equal to 2 power k. I can now divide the set of all the vertices. Let V be written as a disjoint union where how do I know that I can do that? That's clear because n is less than or equal to 2 power k. So I can divide the set of vertices into 2 parts, each one of which has size less than or equal to 2 power k minus 1 because the total is at most 2 power k. You can in fact equally divide if you want to. idea then would be to size of x is 2 power k minus 1. Hence, G sub x, which is the complete graph on less than or equal to 2 power k minus 1 vertices can be expressed as a union of k minus 1 bipartite graphs. Say I can do the same thing for y for the same reason. This is the use of induction. I've used induction here. Similarly on y, is a union of H2k minus 1, where each is a bipartite graph. Can I make a patching operation now clear? That's clear. I can patch them up very clearly. This is sort of so this will have two parts. This will have two parts. Any one patch can be patched up. Let notational be the bipartition. Now I can stick these together, stick those together. Okay. Let xi y to I. y1i, y2i. Then hi with and hi is bipartite. See, what it means is all the edges that occur inside this and inside this, they all have been covered by these k minus 1 bipartite graphs. Now the ones that are remaining are only the things going across. They can be covered by a single bipartite graph. Finally, let hk be bipartite with bipartition then H set of Kn where each Hi is bipartite. So that's for one part of this whole thing. What is the other part? Other part is I have to show that if Kn can be written as a disjoint as a union of k bipartite graphs, then n must be less than or equal to 2 power k. Conversely, let bipartition so it is now we are working the other way around. So I have bipartition for Hk. This is x, this is y. Which of these will cover all the edges inside x? They will be h1, h2 up to hk minus 1. Okay? So we have G sub x, which is complete graph, on x covered by the first k minus 1. Therefore, by what I know is that the theorem is true at the level k minus 1. What that means is the size of x is less than or equal to 2 power k minus 1. Induction. By induction. Similarly, the size of y is also less than or equal to 2 power k minus 1, and therefore the size of v is less than or equal to 2 power k minus 1 plus 2 power k minus 1, which is 2 power k. So this is the best that one can get. There are other ways of proving this, yes. I mean, this is not the. For example, this is saying that n is less than or equal to 2 power k. If I have to prove this theorem, I can take without loss of generality n equal to 2 power k. If I can prove that for n is equal to 2 power k, the first part, then it's clear that if I have less number of vertices, I can. That's okay. That will go through as well. If I can prove something for bigger number of vertices, it's clearly true for smaller number of vertices. Therefore, in the first part, I could have taken n is equal to 2 power k actually. Take the worst case possibility. The largest it can take is 2 power k. Essentially, the same kind of thing will go through. So, let me give an idea. I should work on it. So, when n is equal to, so that completes the proof. what one can do is represent each vertex by binary k-tuple. Each by distinct For example, when I'm talking of K4, and I go coordinate wise, what does that mean? HI is the graph with bipartition xi yi, where xi consists of all those ai is equal to 0. I'm looking at all sequences in which the ith coordinate is equal to 0 and all those in which ith coordinate is equal to 1. This clearly is a partition. This clearly is a partition. There is nothing common between xi and yi. Okay? And hi is a complete bipartite graph with bipartition. This will take care of all possible edges clearly, because if two vertices are different, then they differ at least on one coordinate. In worst case, they may differ only on one coordinate. Then they will belong to only one hi. If they differ at 3 coordinates, then they will actually belong to 3 different his. That's okay. That edge will belong to 3 different his. But this will completely cover, that's clear. Exhaust all the edges. This is a good idea. Okay, using binary tuples is a good idea. Okay, now one more result. I have used this symbol small delta. Have I used this earlier or no? No. Okay, all right. Smallest degree of a vertex. Max. Largest degree. Smallest degree, largest degree. Lemma. Then G has a cycle. Proof. If there is a loop, then there is a cycle. I mean, loops are cycles by definition. By definition, loop is a cycle. Since loops are cycles, we may assume that so if you have a graph that has no loops at all, and if the minimum degree is at least 2, then my claim is there must be at least 2 vertices. It's clear. You just cannot have one vertex, okay, because then you'll have to draw loops only. Okay. Then what is it that we try to do then? Begin with a vertex, keep moving, try to construct a path which is as long as possible. Why would I stop here? Suppose that stop, eventually it will have to end somewhere. Why did I stop here? Because I don't get because by definition of a path, I don't get a new vertex. Why did that happen? But the degree of this vertex is 2, at least 2. Therefore, where is its other adjacency? It got to be somewhere down, and that creates a cycle. That's already a cycle. Is that clear? So write down the proof. I will not write the remaining lines of this proof. I've told you what to do. This just cannot go on forever because the graph by definition is finite. Graph by definition has finite number of vertices. This proof will not work in case you have infinitely many vertices. It does not. In fact, just think of it. I mean, take the set of all integers as vertices with I joined to I plus 1. Okay? This has no cycle. There is no cycle. There is an infinite path, but no cycles. Okay? Now we have an important definition. An Eulerian trail in G is a trail that covers all the edges. An Eulerian circuit is a closed Eulerian trail. Okay, let's see what this is saying exactly. What it is saying is, it's a trail, therefore no edge should be repeated. On the other hand, you would want to go over every possible edge. Now that's sort of a complicated graph. What is the attempt I want to make? I want to begin at some vertex, possibly cover all possible edges. There is a problem now. I cannot cover that vertex. So if I want to be sort of, I cannot really cover that edge. If I want to cover that edge, I could go that way. Then I come back here. But now if I have to cover that edge, I proceed in that direction, these will remain. Then there is a bottleneck kind of situation if I move in that direction. Is that clear? If I move in that direction, there is a problem because I cannot get out of it. Clearly, I just cannot get out of it. But if I don't move in that direction, I cannot really approach that vertex at all. Now, this is the last chance of approaching that vertex. What that means is this is no Eulerian circuit. At the basic level, all the arguments involved here are parity based. At a conceptual level, these are only parity based arguments and therefore are elementary. They are elementary in the sense that they are all parity based. They get more messy in terms of workout. When you work out, actual workout of elementary things can also be very messy. It is like this. The right analogy is, suppose I am the only person living at my home and there is only one door to the flat that I occupy. There is only the front door, there is no back door. And I open that door only when I step out of my apartment flat or when I get in the apartment. That's the only time that door opens. It may happen that I visit the department number of times. I may visit friends many times, but eventually in the morning I may start sometime. I go to several people, I come back home, then visit them again, etc. I come back home at night. Finally, if that is the case, it may happen that on a Sunday I don't step out of the apartment at all. Then the number of times that door will be opened will be an even number. It will be an even number irrespective of how many trips I make. Is that clear? This is the main point. It does not matter how many trips I make. The door will get opened an even number of times. That's because every time once you open the door to go out, you have to return back and therefore you will open it once more. Okay? It just cannot be true that the door will be opened an odd number of times. That will not happen. This common sense understanding is the parity idea hidden behind, that is the idea behind the idea of closed Eulerian trail or Eulerian circuit. So the kind of theorem we are looking for, and I will write down the statement of the theorem. It's clear from what I just said is, if you have a closed Eulerian trail or an Eulerian circuit, then each vertex has an even degree. Each vertex has an even degree. Recall that a loop is supposed to contribute 2 to the degree by definition. By definition that we made, it contributes 2. So the degree of this vertex is 4. Degree of this vertex is 4. Degree of this vertex is 2. Let's write down the degrees. No, degree of this vertex is 3. Degree of this vertex is 2. Degree of this vertex is 4. What about degree of this vertex? 1, 2, 3, 4. What about this? 4. What about this? 2. 1, 2, 3, 4, 5. Is there any mistake? Huh? One with the loop? This is 3. This? 1, 2, 3, yes. Sorry, thank you. Yeah, and this is 2, this is 4, this is 2, this is 3. Anything we have missed out? No, that's it. So there are 4 vertices of odd degree here. If I have to have an Eulerian circuit, then each vertex must have an even degree. This is a requirement. Because of what I just said, you begin at a vertex, you begin anywhere, go along, cover all the edges and come back. Circuit is closed, so you come back to the same vertex. Therefore, number of times you will visit any vertex. Visit means either you get into that vertex or step out of that vertex. That number has to be an even number. It has to be an even number. This is a requirement. This graph has as many as 4 vertices of odd degree. Therefore, it cannot have an Eulerian circuit. where did this whole thing come from? So there is historical reason for calling it Eulerian. This is the famous seven bridge problem. Okay. So what you have is a city in which this is the mainland, there is a river here, that is the other side of the bank, this is the one side of the bank, that is the other side of the bank. There are two islands there and there are 7 bridges. In all there are 7 bridges. The islands are connected to the mainland by one bridge each like this, and the islands among them are connected to each other by 3 bridges, making a total of 7 bridges. In terms of modern graph theory that we look at, this is as good as saying that you have 4 vertices. There is a multiple edge here. I think let's draw it on the other side. Yeah. Yeah. So this is a graph on 4 vertices, 7 edges, in which the degree of this vertex is 5, degree of this vertex is 5, that vertex is degree 2 and that vertex is degree 2. Therefore, from what I said, it cannot have an Eulerian circuit. That's exactly what Euler told the king, that you cannot go over each bridge exactly once and come back to the starting point. If you have to travel over every bridge, traverse each bridge exactly once and come back to the same point where you started, it is not possible to do that. It's just not possible to do it. So the theorem we want to look at G has an Eulerian circuit if and only if at most one non-trivial component are of even degree. What is a trivial component? Sorry? How did I? Sorry? Yeah. Maybe a loop or even an isolated vertex. Yeah, but loops contribute 2 to the degree. Is that okay? Now, I think the trivial component by definition is something that has no edge at all. That has no edge. If you have no edge at all, that means there is only one vertex absolutely without an edge. So it could be, this is an example. This is okay. The requirement here is to go over every edge, not over every vertex. That is not what is asked. So these vertices you can leave them out. It doesn't really matter. How many of those isolated vertices are there? That really is irrelevant because you don't have to go over them at all. What it is saying is there is only one non-trivial component. If you have 2 non-trivial components, then it's clear that you cannot really have an Eulerian circuit because there is no way you can go from there to there. Even if they have degree even, that's irrelevant because there is no way you can go from there to there. Proof. Clearly, let G have an Eulerian circuit. Then clearly G has at most one non-trivial component. Proof here is just follow that Eulerian circuit. Just following the Eulerian circuit, each time you get into a vertex, there is a contribution of 1, and each time you step out of that vertex, there is contribution of 1 more. But this will happen as many take any vertex, as many times you get into that vertex, equally many times you will be stepping out of that vertex. Circuit must make an even contribution to the degree of x d of x must be even. So that is for the first part, okay, the easier part. So what will be the more difficult part? More difficult part is, suppose this condition is satisfied, then I should be sure that there is an Eulerian circuit. Is it okay without loss of generality? We can assume that G itself is connected, okay, because those isolated vertices don't really matter. G is connected with d of x even for all the vertices. Now if your graph is connected in which the vertices have even degrees, then the minimum degree must be at least 2, because all degrees are even. You cannot have a vertex with degree 0 because the graph is connected. G connected actually greater than or equal to 1 Thank you. But it's greater than or equal to 2 because we are assuming that this is an even number. Therefore, the minimum degree is at least 2. Which implies that G has a cycle. So this part will have to be done by induction. Induction on what? Induction on number of edges. Induction on number of edges. If there is only one edge, how would the graph look like? It has to look like that. Okay. Does that have an Eulerian circuit? Yes. That edge itself. In fact, for this problem, loops don't really matter. Loops don't matter. Do you see that? I mean, it really doesn't matter how many loops you have. It is not the loops that cause the problem. The problem is caused by edges that are non-loops. The entire problem is not because of loops. Loops don't give any trouble at all. I could have removed that loop actually. Doesn't matter. All those loops I could have removed them. Say C. What I would then do is remove the edges of C from G. Let be the subgraph with edges of G removed, edges of C removed. H may not be connected. H may not be connected. G is connected doesn't mean that H is connected. So we have to be a bit careful. So let me draw a picture here just to see. Out of that, I have located a cycle. So the yellow edges are on the cycle. So if the yellow part is gone, this really gets divided into components. So H has components. One component is this left part here. This is one component. This is other component. That is that squarish thing is the third component, and that is the fourth component. All the vertices are to be retained. All the vertices are to be retained. But the point is, when you remove all the edges on the cycle, degree of each vertex either will remain the same like this. This vertex has degree 4. It remains the same even after removing that cycle, or it gets reduced by 2. It gets decreased by 2. Therefore, in H also all the degrees are even. In H also all the degrees are even because you're either keeping the same number or you're subtracting 2. Okay, what is the notation? dgx means its degree in x, its degree in G, degree in H. H will then have components what is the property of each one of these components? Either that component could be trivial, in which case there is no edge in it at all, in which case you can ignore it. You can just forget about it. The component happens to be trivial, there is no edge there to be covered, I don't need to bother about it. Okay? Or if HI is connected, each HI is of course connected. If HI is non-trivial, then connectedness of HI implies that HI has an Eulerian circuit. All these Eulerian circuits, I want to stick them together, form Eulerian circuit for the big graph. Okay. How do I know that HI has an Eulerian circuit? Induction. That's exactly where I've used induction. You removed edges, therefore number of edges in HI is smaller, clearly the number of edges in G. You have certainly removed at least one edge, the worst possibility. So that cycle has edges that have been removed. Move on the cycle. Each time we get a vertex of complete an Eulerian circuit in HI and get back to the same vertex. In C, I know how to move. That is something I know how to move. There are in fact only two ways of moving in C, either clockwise or anti-clockwise. I can just choose direction. For example, I can choose to move this way, this way. What has happened here is, this is the, before I begin itself at this vertex, I have a component. Go in that component is even, non-trivial, connected, even, therefore I have a prior knowledge that there is an Eulerian circuit in this. I know how to obtain an Eulerian circuit in this. Then continue that way. Get back to that vertex. You get to this vertex, you see that there is a component, go that way. Get back there. Then you move here, follow the loop, come back, then traverse back. Okay, so this is doable. So the whole point is this is doable. Thus, we can complete an Eulerian circuit. As I said, as an idea, it's quite elementary. It's very elementary idea. It's just that in terms of working out, it can be messy. It can be messy when one is really confronted with the question of go ahead, find out an Eulerian circuit. It can be messy. Okay. This is more descriptive proof of Euler's theorem. Incidentally, this theorem is Euler. Yeah, sort of beginning of graph theory, 1736. Seven bridges problem, Königsberg bridge problem. That is exactly what that problem is. Then G has a path. These are standard proofs in graph theory. Okay, what is meant by standard? What is it that I do? I want to construct a path whose length is at least k. So I would say we're talking of simple graph. There are no loops here. This statement will not be true in case there are loops, because I can just take one vertex and keep drawing loops around that vertex. So this is false in case your graph has loops. What you do is, you look at a path whose length is as large as possible. So let P be a path with largest possible length. Why is it that I cannot extend this further? Why did that happen? Why not one more? Because no. So where are the vertices adjacent to y? There's only one vertex adjacent to y here. Where are the other vertices? They all should be here. Okay, they all must be here. Adjacent to y are in P. How many vertices are adjacent to y? At least k. Therefore, there are at least as many as k vertices here other than y itself. Okay. So on this path, I have at least k plus 1 vertices. So P has at least k plus 1 vertices. That is, P has length at least k. With a slight modification, you can, which will continue in the next lecture, you can also create a cycle. If that number k is at least 2, then you can get a cycle whose length is at least k plus 1. Okay? It's essentially the same argument. You can create a cycle. In fact, you do, because the moment you say y is adjacent to all these vertices, obviously you are creating cycles. The claim that we have is the cycle should have length which is as large as possible. Therefore, there should be a leftmost vertex which is adjacent to y. That will create a cycle which is as long as possible. So with that theme we will continue in the next lecture. Thank you.